So for this
all
one,
of them to pay for part of
The government will.
okay, we'll look at this one. So this is the circular. You remember in the kind of the circular ring, in our previous exam, the test, I make a short cut. I make a very narrow cut there. The same type of structure. Okay, so for this one, if we have under the transverse loading, so for this case, the transverse loading is assuming applied vertically. So this is in topology. In mathematical topology, this is the same as the U shape. We call it topology. That means all the configurations into the space won't tangle. Okay, that's called the topological equivalent. So for this case, the shear center is outside here. Okay, so that is a common sense. Hopefully, right now I help you to build up the common sense. In this kind of things, the shear center should be always on here. Okay, that is the only place we have. So literally, we locate here that we want to calculate the distance from the center of the ring. So for this case, that is the same thing. We do the calculation. Then, for example, here we are assuming the loading is applied vertically. Okay, and then using our strategy. So the V times E by taking the moment about, for example, about the center here, the center is called C, equal to 0. So that means VE will be equal to whatever the shear flow. For this case, the shear flow in the vertical portion must be aligned with the V. So the shear flow will be in this flow direction. Okay, counterclockwise directions. So the first one, you have to identify the directions of the shear flow correctly. Okay, so now we have this one, then we simply calculate. So that will be equal to the tau dA, that is a total force, and multiply with whatever the distance, right? Whatever the distance. Okay, the concept is like this. Okay. So now for this one, this is a ring, and we can try to make is this.
Sorry.
Okay. So let me pick up a segment for Q. So this is the center here, and if vertically, then this is our neutral axis. So now we want to calculate Q. That will be equal to the shaded area multiplied with the distance of the centroid of the shaded area to the neutral axis. So here, let me call the y bar. Okay. And here we're interested is the shear flow here. So that is the shear flow. So in this way, the thickness equal to T. The thickness equal to T here. Okay. So that is the thickness here equal to T. And we need to calculate I. I is the moment of inertia about the neutral axis. Okay, and V is given. So basically, we have almost everything ready. Then we implement the details.
Are we just going to use the rectangular formula for an area?
No.
Okay.
No.
All right.
So now we figure out the I. What is I first? Okay. I about the neutral axis basically is the 1/2 of the J. J is our polar moment of inertia.
And C
Yes.
outside.
Yes.
And
Yeah.
squared minus C.
So
or
here
no, to
we
the
can,
fourth. Is it
yeah,
to the
we can
fourth?
approximate into this one. So here the center is half of the center is A. So the outside, the CO equal to A plus T over 2. The C equal to A minus T over 2. So therefore, the J equal to 1/2 pi and CO to the force minus C into the force. We simply plug in this into this formula. Okay, so that one, I have calculations here. So that is over 2 A plus T over 2 to the fourth power, A minus T over 2 to the fourth power. This one, if we do this correctly, and this one will be equal to pi.
Did you do it correctly?
Weird. Let me do this quickly. I believe my calculation is right. Okay, so if we expand this and fully expand it, then the coefficient will be like something like this one. So we do this one carefully, then that will be equal to pi over 2 and 4a squared t plus a t to the cube.
And that's just J.
Can I borrow your pen? I have the mistake here. Thank you. Thank you. Okay. And now, compared to the dimension, A is much bigger than the T. So this one approximates equal to pi over 2 times 4A cubed T. So then, therefore, the moment of inertia about the neutral axis is 1/2 of this one. So that is A squared T. So we use this one.
Wouldn't the pi still be there?
Oh, pi, yes. So this one is equal to pi times A squared. So now we calculate Q. The Q for this shaded area, and here we I can provide you the formulas here. So we have two cases, circular. So if this is an entire occupied materials, we call the circular sections, and centroid somehow is here, and that one, the distance to the center of this circular section, this is x bar, and that one, let me call it r bar, okay? So this is the center. So this one is 2r sine alpha 3 alpha alpha is half of the angle here. The radius of the circle is r. For arc, and that is the one-dimensional geometry and with thickness very insignificant the width. Okay, so this is the arc here. So that means the materials only occupy in the very thin arc. Okay, and this is a centroid. So that r bar equal to r times sine alpha divided by alpha. For our case, I follow up the publisher's solutions since they picking up this. Since they are picking up this formula, they assume that the T is very, very thin compared to A. If T is thick enough to make this thickness dimension compatible with A, then we have to pick this formula. We simply subtract one big piece. We subtract the smaller circular piece from the big piece, and then we would have this circular ring coming out, right? So that is the formal procedures.
Which one do we use? Do we use both?
No, here for simple way, I will pick up this one. Okay, so here we assume the T is very small. So here we assume T is less than A. So we pick up the circular arc formula. Okay, so for this case, therefore, R, simply by noting this notation here. So this is the distance, and this is our R bar, right? Okay, this is a centroid. This representing is a centroid of this one. So for this case, R bar is equal to A times sine alpha alpha. And again, for this piece, this is alpha. Okay, alpha is the angle from the center, the bisecting middle line to. So here the y bar naturally equal to r bar times sine alpha, right? Okay. So this one will be equal to A times alpha sine square alpha. Okay, so now we're almost ready. So therefore, Q will be equal to the area. The shaded area basically equal to, assuming this is the A times radius times angles, and that is N times T. So this is the area, and multiply with y bar. Okay, so this one is the area. This one is y bar. Area simply this one, A times 2 alpha. The radius times alpha give us the length, arc length, right? Arc length multiplied with T give us the thickness, give us the area. Okay?
So A times 2 alpha is the arc length.
Arc length, yeah. So now with this one ready, and then this one basically is equal to A squared T times 2 sine square alpha. And here we're using the trigonometry, and basically the 2 sine alpha can be even simplified into cosine.
Will it be when? Don't forget the square. Oh wait, no, never mind.
No. Okay. now with this everything in place, then we can begin. So right now here we pick up locations. This location is where we calculate for tau. So therefore tau equal to VQ over IT. V here we fix the Q is the function of the alpha, 2 alpha. 2 alpha basically is measured from here. This is 2 alpha, right? And we make that easier. Why not we give 2 alpha equal to theta? The theta simply measured is the radial location of this section we measure. Okay, so basically this is a function of theta. I fix, T fix. So in this way, we simply calculate its tau. We do the area integral. So now we fix the shear stress here. This is our shear stress around here, and this is the small area. And what is small area? And that would be equal to T times radius times d theta. The small length, the small arc length is a d theta, right? So this one tau times dA. dA is T times a d theta. We do the integral for the area from theta equal to 0 degrees to how many? It gets a whole 2 pi. Or if you wish, we can only get into, okay, here is 2 pi. Are we okay? Okay, so this one will be equal to the calculation carefully, this one will be equal to so this is our small force. And wait a moment, I want to right now fix this concept here. This is the shear force, and the distance, this one again, to our formula here, that is a moment balance. This one is to take a moment about the center here. The center is here. And right now we have a small force. So right now I want to fix that area, and that distance basically come into is, yeah, I think that's the same. Okay, so let me fix this one here. So that is 2 pi V okay, so we plug into here in these equations, then VE will be equal to, right now this is the force, 2V, and this force you can see that is circulating and always has the constant distance about the point we take the moment. So this is times A. Again, here we take the shear flow or shear information is about the circulation here. It always a constant distance with the center here. So we take up the distance is a constant. So from here we can calculate E will be equal to 2A. That's it. Okay. And so that is for this question.